Hello guys, this is our second lecture and we're going to talk more about number system and number codes. So let's begin. Okay, we had a recap on what we have learned on last week. Let's now talk about complements of numbers. There are a few more topics that we have to get familiar with. One of them is complement of numbers, so we can uh, learn how we can digital circuits and what are their applications in actual circuit design. Complements are used in digital computer design to help us simplify the subtraction operation and for logical manipulation. Simplifying operations helps us to build build simpler and less expensive circuits that can help us to implement the operations. There are two types of complements for each base R systems, the diminished radix complement and the radix complement. Now let's talk about the diminished radix complement. To find the diminished radix complement of a number n which has base R and it has n digits, we use this equation. So we have two examples here. So this number, we call it n. It has lowercase n equal to 6 because it has 6 digits. So, and the number is in decimal. It has r equal to 10. It's in base of 10. So looking at the equation, 10 power 6 minus 1 minus the number, which is the 546,700, we find 453,299. Using the same, this is the diminished complement or r minus 1's complement of n. So we can find the r minus 1's complement of this number using the same equation. For a binary number, I provided two other examples. So in binary system, r is equal to, because we only have 0 and 1s. Here we have 0, 1 up to 9, 10 numbers. That's why r was 10. So r minus 1 is equal to 1, and we have 1, 2, 3, 4, 5, 6, 7. So let's see how we can find the r minus 1's complement of this number. So 2 power 7 minus 1 is so 2 power 7 is 128. The binary representation is 1, 1, 1, 0, 0, 0, 0, 0. Okay, and we subtract 1 from it, we get 0, 1, 1, 1. These are the calculation we have learned last week. So 1, 1, 1, 1, 1, 1. So we have to subtract n from it too. So n was 1, 0, 1, 1, 0, 0, 0. So what's the result? We get 1, 1, 1, 0, 0, 1, 0. So this is how we can come up with the r minus 1 complement of a binary number. So if you look at the result to find the r minus 1 complement of a binary number, the only thing you have to do is just change zeros to 1 and change 1s to 0. This is the calculation and this is the equation that you can follow to get the same thing, but by just changing the 1s to 0 and 0s to 1, you can find it easier. Let's see how the R1's complement can be found. So now let's see how we can find the radix complement or R complement of numbers. So compared to the diminished complement, which we had r minus 1, we have the equation changed to r power of n minus our number. So let's see how we can find the r complement of this example. So r is equal to 10. Using the equation, we have 10 power 6 because we have 6 digits. 0, 1, 2, 3, 9, 8. We get 987, 602. We can follow the same steps to find the R complement of this number, which is 753300. So how we can find the 2's complement, which is a very important part in the digital system design. We're gonna talk about it more in future slides. Oh, this should be 2 actually, because it's a binary number and binary is of base 2, which means R is equal to. So for the first number, we have 7 digits. So we have 2 power of 7 minus our number. If we convert this binary number to decimal, we get 108. The answer is 20. If we convert 20, which is of base 10, we get 0010100 in binary, which is our answer. You can follow the same steps to find the answer for the second example, but there are two alternative, there is another alternative way which you can use to find the base 10 or base 2 R complements. So let's solve this example, the second part of the base 10 example, using this alternative way. Leave all least significant zeros unchanged. So the right digit, the digit on the right, which is 8 here, we call it least significant. And the 1, as we go to the left, the level of significance gets higher. So this one is the most significant. So leaving all least significance unchanged, zeros. So we leave these 2 zeros unchanged. Subtract the first non-zero least significant digit from 10. First non-zero least significant digit is 7, non-zero. We subtract it from 10, we get 3. Subtract all higher significance digit after 7 from 9, which means 2, 4, 6. If we subtract them from 9, we get 7, 5, and 3. This is how we can use the alternative way to find the R complement of numbers in base 10. So how about the base 2 numbers? This one also has an alternative way. So leave all least significant zeros and the first one unchanged. So we have 2 least significant 0 and a 1 after that, which we want to leave unchanged. We take it to our solution, replacing 1s with 0 and 0s with 1. So we have 4 other digits remaining. We change 1s to 0 and 0s to 1s. And this is the alternative way of doing it. So the ordinary method of subtraction we learned in the elementary school, where we used to borrow a 1 from a higher significant position when the minuend digit was smaller than the subtrahend digit, does not actually work in the digital systems. The use and the application and the purpose of complements is to make it more efficient in digital hardware and actually make it doable in digital hardware, because we cannot use ordinary subtraction methods. So to do this subtraction of two n-digit and unsigned numbers m minus n, we can follow these steps. So first we add the minuend m to the r's complement of the subtrahend n, this way, using this equation. So in case that m is greater than equal n, this summation will result to an end carry which is equal to r power n, which we can easily discard, and we will be left with m minus n in the end. In case that m is less than n, this summation does not produce an n carry and will be equal to this, which is equal to the r's complement of this number. So these two are equivalent. So we can just take the r complements of the sum and place a negative sign in front. So let's see how these examples can be solved. Now let's have a look on these examples. So we want to use the 10 complements to subtract 3250 from 72532. So from the previous slide, we know that we have to first find the tens complement of n. So this one is n and this one is m. Forgive my handwriting. I haven't got my writing pad yet. So n is equal to 4 because it has 4 digits, and r is equal to 10. So we get 10 power of 4 minus 3250, which gives us 96750 here. So now we add the minuend m to the r's complement of the subtrahend n, following the first step in the previous slide. The answer is 169,282. So just because the result has produced an end carry equal to r power of n, it means that m is greater than equal to n, which means our result is positive. Now let's have a look on the second example. We want to subtract 72,532 from 3250 using the tens complement. So we're gonna add the minuend m to the r complement of the subtrahend n. So the r complement of n is 27,468, and if we add these two together, we get 30,718, 30,780. So do we see an end carry equal to r power of n here? No, we don't. So what does it mean? We don't have an end carry. So what does it mean is that the answer is negative. So following the third step in the previous slide, we can obtain the answer in a familiar form by taking the r complements of the sum. We take r complement of sum, which is 30,780, and then we put a negative sign behind it. So r complement of this number is equal to what? Is equal to 69282. And just because we don't see an end carry like we saw in the previous example, it means our result should be negative. So remember this, that when we are subtracting using the complements, we find if the answer is negative from the absence of the end carry and the complemented result. And this is how we realized in this example that the answer should be negative. Using the complements to perform subtraction in binary numbers also follows the same procedure as we discussed in previous two slides. So if we want to subtract y from x, so we get the 2 complement of y, which is equal to 0, 1, 1, 1, 1, 0, 1, and we add them together and we get this result. So we are observing an end carry here, which is equal to 1, 0, 0, 0. So we have to discard that end carry, which gives us 0, 0, 1, 0, 0, 0, 1. And this is our result, which should be also positive because we have observed an end carry. In the second example, getting the 2's complement of x and adding them together, we don't observe any end carry. So it means that this one is a negative answer. So we know that in basic mathematics, we show positive numbers with a positive sign and negative numbers with a negative sign. But in hardware design, due to the limitations that we have, we don't have positive and negative signs. We only have 0 and 1s. So how do we represent a positive and negative number in digital computers? So there's an approach called sign magnitude representation, which assumes that 0 stands for positive and 1 stands for negative. So if we look at this binary number, we can assume that it's equal to 9 if it's an unsigned number, and if we think that it's a signed number, so 0 stands for positive, and it's equal to positive 9. Looking at this example, this is equal to 25 if we convert it, and if it's a signed number, 1 was negative, right? So it's negative 9. So in this sign magnitude representation, it assumes that a number has two parts. The first one is the actual digit, actual number, and the leftmost part represent the sign of the number. And it has some disadvantages, which I'm gonna tell you guys about in next slide. The other approach is signed complement number, which represent the positive of a number the same way that we show in sign magnitude, but shows the negative it shows the negative or the negated number by taking its complement. If we look at this example here, assuming that the number is 9, when we are showing 9 in 8 bits, sign complement assumes that this represents positive 9. And to show the complement of 9 and to show the negated or negative 9, it takes 1's complement and 2's complement. Both approaches can be used to find the negated of integer 9. But the 2's complement is most common use because it needs less hardware and it makes the design simpler. But let's see why the signed complement approach is better than the signed magnitude approach. We have a comparison here to see what are the differences of signed magnitude method and 2's complement methods. And we mentioned that the advantage and the purpose of complements is to help us design more simpler circuits. You see that if we follow the sign magnitude method, addition and subtraction are performed on separate hardware devices. But if we use the 2's complement method, addition and subtraction can be done only using a single adder circuit, which we learn about this later. And in 2's complement, it considers number as a whole, while sign magnitude considers that number is divided into two parts, the sign and the rest of the number. And this table shows three different representations of these decimal numbers, and we see that for positive integers, all three categories show the same number because in positive they look like each other, but in the negative part, the sign magnitude just puts a 1 here to show that it's a negative number, but in sign 1 and sign 2, they find the negated integer by taking the complements of these numbers, and these are the complements of the positive integers. So the arithmetic addition of signed binary numbers follows the same basic mathematics. Adding a positive number to another positive number gives us a positive number, and adding a positive number to a higher negative numbers gives us a negative number, which is in the two complement form. If we use the two complement form of negative number here, our result is in also the two complement form. Adding a negative 6 to positive 13 gives us a positive number. Negative 6, negative 13 gives us a negative 19, which also is in the 2's complement form of negative. And if we have a carryout bit in the sign position, we have to discard it because we want the leftmost bit to represent our sign. So we mentioned that just because we're using the 2's complement, addition and subtraction of signed binary numbers can be done only using a single device. To do the arithmetic subtraction of signed binary numbers using the 2's complement form, first we take the 2's complement of the subtrahend, and we also include the sign bit, and then we change it to the addition, and we add it to the minuend, and we also include the sign bit. If we have a carryout sign bit in the position of the sign bit, it should be discarded because we need our sign bit in the leftmost position. So we have negative 6 minus negative 13. So the two complements of the negative 6 minus the 2's complement of negative 13. So we take the 2's complement of negative 13 which is this one, and we change negative to positive based on these steps. And then it becomes a simple addition, and we get this, which is equal to positive 7. And we know that this 0 means positive. We know that binary number system is the natural number system for computers, but most of the people are used to decimal numbers. One way to resolve this difference is to convert decimal numbers to binary and perform all the operations or arithmetic calculations in binary and then convert it back to the decimal. This approach requires that we store decimal numbers in the computers so that they can be converted to binary. So because the computers can accept only binary values, we should represent the decimal digits by the use of a code that can contain 0 and 1s. It is also possible to perform all the arithmetic operation directly on the decimal numbers when they are stored in the computers in a coded form. A number with, there is a coding approach, a way of showing binary numbers in code, which is called BCD, which a number in this coding format, a number with k decimal digits, assuming this number k is equal 3, is represented in BCD form with 12 bits as 0011, 1001, and 0110. And each group of 4 bits represents 1. So this one is 3, this one shows 9, this one shows 6. Now let's see another example, 185. So the BCD form is 0, 0, 0, 1. In BCD, where this one is 1, 8, 5, and is equal to the binary representation, which is 1, 0, 1, 0, 1, 1, 1, 0, 0, 1. From this example, we see that the BCD code requires 12-bit to represent this decimal number, but the binary version requires only 8-bit. It should be known that the representation of a BCD number needs more bits than the equivalent binary value. But we should know that there is an advantage in the use of decimal numbers because computer input and output data are generated by the people who uses the decimal system. It is also important that we know that the BCD numbers are decimal numbers and they are not binary, although they are represented by bits and 0 and 1s. The only difference between a decimal number and BCD is that decimals are written with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the BCD numbers just use the binary code 0, 0, 0, 0 to show 0, 0, 0, 0, 1 to show 1, and so on. And so the decimal value is exactly the same. And the decimal value of 10 in BCD, k is equal to 2, is shown using 10 bits. And here is another example. So we should consider BCD as a decimal representation, decimal value, and not a binary value. It only uses 0 and 1s, but it's not a binary value. Now let's see how BCD addition works. We have 3 examples here. So we add 4 and 5, which their BCD equivalent codes are these two, and the result is 9. We need to be really careful that the results of our BCD addition is represented using only these 10 BCD codes. Anything beyond this number is an invalid BCD digit. Anything like 10, 11, and so on. In the second example, we add 4, which is a valid BCD digit, with 8, but the result is 12. We said that anything beyond that is invalid. So we have to convert it back to a valid BCD digit. To do that, we add 0, 1, 1, 0, which is equal to 6, and we get a valid BCD digit and a carry bit. The reason to add the 6 is that the most significant bit position of the binary sum and the decimal carry differ by 16 minus 10 is equal to 6. This is the reason why we add 6 in case that the result of our addition is more than 9. For the third example, we add 8 and 9 together, we get 17. So we have to make it a valid BCD digit. We add it to 6, which is equivalent to 0, 1, 1, 0, and we get a valid BCD digit 0, 1, 1, 1, and a carry bit. Now we see this example, which is much more illustrative. We want to add 184 to 576. So 184 added to 576 6. The result of 6 and 4 is 10, which is not a valid BCD digit. 8 and 7, this one is also invalid, but only 1 and 5, which is equal to 6, is a valid BCD digit. So we keep it as is in the result in our summation, but we have to convert these two back to these BCD valid digits. So we add them 6 binary digits of 6, which is equal to 0, 1, 1, 0. We forget about the carry bit, and we have our BCD valid digit. And here also we add this one to 6 again, and we discard the carry bit, and we get our results, which is equal to 7, 60, or 0, 1, 1, 1. In BCD form. There are other forms of binary codes rather than BCD, which are 2421, XS3, 84, -2, -1. And for each of those, these range are the valid codes, and these are the invalid range, that when we see, it means that there is a problem that we have to fix. For BCD, if you remember, we would add 6 or 0, 1, 1, 0 to convert it back to a valid BCD digit. Gray code is another form of binary codes, which has the range of 0 to 15. And in this table, we also can see the range of valid binary codes in terms of gray code. Now that we talked about the theoretical part of the digital systems, let's talk about the physical components too. Binary cell. Binary cell is a physical component and a device that has two stable states and is capable of storing one bit of information, which could be either 0 or 1. The input to this binary cell is a signal telling the binary cell to have the status of 0 or 1, and the output is a physical quantity that can distinguish the state of the binary cell. If we have a group of binary cells together, we can form a register. A register is actually a group of binary cells, and a register with n cells can store any discrete quantity of information that contains n bits. So what does it mean? So assume that we have 4 binary cells. We can have a register where each of those binary cells can take either 0 or 1 as their states. And this register can have 2 power of 4 number of possible states. So a digital system is known by its registers and the components that perform data processing and data transfers. When a register in digital system, a register transfer operation is done when a basic operation that consists of transfer of binary information from one set of registers is done and is transferred to another set of registers. This is what we call register transfer. Let's see an example of how it is done. This is an example of register transfer of information in computers. We have a keyboard that sends signals to the registers. It could be a key that is an input to the binary cells of each register, and they are sent to the memory unit to be stored in the memory register. And see that this is the binary representation of character J, character O, and character H, character N. And we said that the inputs to binary cells are the signals coming from other sources, which in the case is a keyboard. And this process happens periodically whenever there is an input to the system, like pressing a key on the keyboard, moving your mouse, or anything like that. The other term in digital design is binary logic. Binary logic is made of binary variables and a set of logical operations. Those binary variables are the input and output of these operations, and the operations are and or not. So we see one by one what does each of those operations do. The first one is AND operation. This operation is represented by a dot or by the absence of an operator. So uh, this way we call it X and Y, X and Y. And this is how we interpret and we call them X and Y. And Z is the output of this AND operation. So this operation is interpreted to mean that Z is only 1 only and only if X is equal to 1 and Y is equal to 1. Both of them should be equal to 1. So X and Y is equal to 1 means Z. And otherwise, if either of these two variables are 0, Z is equal to 0. The OR operation is represented by a plus sign, and we call it X or Y. So for this case, when either of X or Y are 1, the result of this OR operation is 1. And also, if both are 1, again, the result is equal to 1. And the last operation is NOT. This operation is represented by a prime sign. For example, X prime is equal to Z, or we represent it by a bar over the variable. And we call it not X equal to Z, meaning that Z is what Z is not. In other words, if X is equal to 1, then Z is equal to 0. If X is equal to 0, Z is equal to 1. For example, let's assume that X is equal to 0. X not equals to 1. If X is equal to 1, then X not or X not, the other representation, are equal to 0. And these are the three binary logic operations that we're going to really work with them, and we're going to have a lot of interactions with them in this course. There's a table that makes it easier for you guys to see different examples of doing operations on AND or using AND or and NOT operations. So see, for the AND operation, which we show this way or this way, if both X and Y are 0, the answer is 0. The results of AND operation 0. Whenever only one of them is 1, again, the answer is 0, but only if both of them are 1, the answer is 1. For OR case, if both are 0, the answer is 0, and we only need one of these variables to be 1, so the result of the OR operation is equal to 1. For the NOT case, when X is equal to 1, X not is, when X is equal to 0, I'm sorry, X is 1. When X is equal to 1, X not is equal to 0. Logical gates are the graphical representation of AND, OR, and NOT gates. We have three logical gates which we use to demonstrate the logical operation in a circuit. The first one is AND gate, This one is OR gate and this one is NOT gate. The input to these logical gates are those variables we have mentioned earlier, and the output is this output signal, which we call it Z, which is based on the type of operation these gates do. The inputs to these gates are these variables and inputs are actually signals. So if we have x is equal to 0 and y is equal to 0 as our input signal, the output of logical gate AND will be 0. For this case also is 0 only and only if both input signals for AND gate, I mean x and y, are 1, we see an output of 1. And in any other cases, the output signal is 0. For the OR gate, if we have input signals both equal to 0, output is 0. If either x or y are equal to 1, our output signal will be 1, and only if both are equal to 0, we get 0. And for the NOT gate, whatever we feed into the NOT gate, we get the other form of it. If the input is 0, output is 1, input is 1, output is 0, input is 1, output is 0, output is 1, and for this one, output is 1. So this is another example of how those logical gates are working. There are more complex forms of AND and OR gates where they have more number of inputs. We remember that the normal AND and OR gates had 2 inputs, signals, but this one has 3 variables or 3 signals, and this one takes 4 signals. And later we're gonna see how basically they handle those variables until they find the result. So I can just you can just imagine that for the AND gate, f is equal to 1 only and only if all 3 inputs are equal to 1. In any other cases, it's equal to 0. And for the OR gate, G, which is the output, is equal to 0 only in the case that all 4 are 0. Only if one of them is equal to 1, G would be equal to 1. So we're at the end of our second lecture. You're gonna have your first homework on Thursday posted on the Blackboard. You have until Monday midnight to submit the solutions to the homework back into the Blackboard. Please send me your questions or join the office hours from 4:30 to 5:30 Tuesdays and Thursdays. If you had any questions or concerns about the course, just let me know. Thank you.